Oh, I guess. Okay. Does that pop up a window in everybody's house that says, "Is it okay if I record you?"
Yeah, I think so.
Okay.
It popped up for me at least.
Okay. All right. So if there's no business, then I'll just get started. And I actually have a lot to talk about today. As I thought I'd only spend one day on compound transistors. And then I thought it would be fun to have you figure out how to improve amplifiers and output stages and input stages now that you know about these compound transistors, and let you just improve these circuits we've been looking at. So I got excited about that, and so we ended up doing that on Wednesday. But that put actually I didn't remember about the having the diff pairs on the homework as well as I should have. So what I'm going to do is I'm going to do diff pairs first, and then the second topic that you need for the homework. It's pretty quick once you see it. So that, I think if we have 5 minutes, I can go through that. So, but first I just wanted to get solidly through the diff pairs. And diff pairs are what stage of your circuit?
The first stage?
Input.
First stage, input, yes. So Spencer's looking different today. So we're finally getting to the input stage. So we had common emitters and common sources for the gain stage. This is a big gains. And then we had the common collector or the push-pull for the output stage. And now we're getting to the input stage. So that gives you all the tools you need to build a complete, pretty good op-amp. So let's look at, we're going to go with, pen's not working, of course. Okay, let's try it with this. And so it's supposed to be a resistor. Since I'm drawing with the mouse, I'm gonna cheat. And I'm putting, in lab, you probably have this as -5 volts. I'm putting this as ground for our discussion today. If it was, if you wanted to convert the things I say today to -5 volt to +5 volt, just shift everything up. So for example, in lab, this is -5 volts, that's +5 volts, and you give this 0 volts here. If I make this ground in 5 volts, now this goes to 2.5 volts. So before 0 was halfway between 5 and -5. If you switch this to ground, now this needs to be halfway between ground and 5. So do this, and I'm going to give you the names. At some point, the pen will start working again, I think. And we'll talk about why this is V out plus on the side. So we've got V in minus over here. So you'd think V in minus should go on this side, but actually that's not how it goes. It's what the plus means here is that it goes in the same direction as the plus input over here. So if V in plus goes up, V out plus will go up. And if V in minus goes up, then V out minus goes up. But those VI plus going up and VI minus going up won't happen at the same time. And I'll explain that in a minute too. I got ahead of myself already. Okay, so let's start with basic definitions. I really want my pen to work. There's a lot of writing. Nope, it's just not going to work today. Okay, so one is that have this thing called VID, and that's the input, that's the voltage in differential. That's what the D stands for. And what that means is the definition of VID is let's do it this way. Yeah, no, that's okay. VID equals VI plus minus VI minus. And notice I wrote these in lowercase. There's the big kid version of this too. So VID it's VI plus and VI minus. It's the difference between the two. And you say, well, wait a minute, what's the difference between these two? Notice I had a capital letter first. So this is actually some DC voltage. Well, I'm going in the complete different order than I planned on going. This is VIC plus some delta V. And this right here is that same VIC minus that same delta V. And I actually wish, if this was a video, I would start over at this point. But I'm going to try to save myself here. This VIC, remember over here how we set this to say this is going from 0 to 5 volts? So we'd set this to 2.5 volts. And then we'd move it either a little bit up or we'd move it a little bit down. So you'd take VI plus and move it up and down. And there's some DC voltage. There's some DC voltage that you're moving it above or below. And that DC voltage is this VIC. So it's basically the offset of VI plus and VI minus. Both of these have the same offset, and then they're moving above and below that voltage. Okay, so VIC is the offset for the base voltages, these two transistors on the side here. Okay, and then why I wrote this as a minus and this as a plus is because there's this thing called a balanced input. And what that means is however much VI plus goes up, VI minus goes down by that same amount. So they're equal and opposite changes. When they're the same, they're both at VIC. So that's the default. That's where they sit when no signal's being put on them. But when you move the signals, when you move VI plus up, VI minus has to go down, and that's called a balanced input. Okay, so that's what I've drawn here: VIC minus some delta V and VIC plus that same delta V. So these two delta V's are the same. So what that looks like is this might be VI minus, and then this would be VI plus. And that average, there's an average value here. So if you took those two signals, added them up, and then divided by 2, you'd get VIC. Okay, so now I think I'm where I was trying to go. Any questions on that definition? VID, so I've seen three definitions now. I've got definition 1, VID, definition 2, VIC, and definition 3 is a balanced input. One of the most difficult things, I said this in the video, which I thought I posted, but I didn't see. One of the most difficult things about diff pairs is that there's so much new vocabulary. So, so far we've had three new vocabulary words. And in lab, you didn't use a balanced input, you used an unbalanced input. And what that does is, and then VI minus would be here. So this would be VI minus. This would be VI plus. So whereas a balanced input goes like this, an unbalanced input goes like this. And that's what you used in 347 and in the diff pair lab this quarter, if you've already had it. And the reason is just that we don't have the equipment to give you a nice balanced signal. But in real life, these circuits generally get a balanced input, not an unbalanced input. Later on, we'll get to the math, probably not today, why balanced inputs and unbalanced inputs basically give you the exact same gain. But if we have time, we'll get to that. But for now, just take I hate to say it, but take my word for it that both of these give you about the same gain. Okay, so we've got a new term here, unbalanced input. So now we've got VID, VIC, balanced and unbalanced. Any questions on those terms? I can't see people's faces, so.
That makes sense.
Okay, thank you. All right, if there's a VID, what else do you think there is? What do you think VOD is?
Somebody who overdosed on voltage.
When you've overdosed on voltage? Is that what you say?
Yeah.
Okay.
The output differential?
I'll take the second answer, just so I don't get in trouble. Yeah, so that is your V, not I, output plus minus your V output minus. And let me just go back again. If you look at VID, when you subtract VI minus from VI plus, do you see that the VIC goes away? And it's just that it ends up being 2 delta V. When you subtract these balanced, or if you subtract the two inputs, the DC part of it goes away. So VIC actually gets subtracted out. I'm sorry, I interrupted you.
Oh, no, I was just gonna say that makes sense to me, since like they're just like adding delta V and subtracting delta V. So if you took the difference, it would just be 2 delta V. That
Yep.
makes sense.
Exactly. So, and that is actually part of the magic of these circuits, that if this VIC changes, in other words, the offset on either side, it actually doesn't make a difference in your inputs or outputs. It's the superpower of this circuit. So let's keep going here. So the same thing here. So here's another term here. It's the output differential. And again, on the output, V out plus actually equals some average value, some offset. It's not I keep wanting VOC plus some delta V out, and the V out minus equals that same offset minus that same delta V out. Okay. And so we've got VIC and VOC now. So those are 2 more terms we've got. And they are just the average of the 2 signals. Okay. So you've got some offset, which is actually the average of the 2 signals. And to get the input, you add a little bit to one side and subtract that same amount from the other side for the output. It also has this average, this VOC, and you add a little bit to it or subtract from it to get the actual output signal. And when you subtract these two, again, VOC goes away. Okay, so the definition for differential signals, even though we don't know what VIC and VOC is yet, other than that it's the offset. Are the differential definitions okay?
Sorry, Professor, what did you say VOC was again?
VOC is it's like, I haven't defined it yet, but it's VOC is the average, because by definition, your output is some average, some offset. On one side, it gets plus a delta V, and the other side gets minus a delta V. It's the average of the two signals.
Okay. Okay, thank you.
Okay. So number 3, let's figure out what VIC is. VIC is input, V input common mode. And that actually just equals, as I said, it's the average. You can think of it as the average, or you can think of it as the offset of the input signal. Okay, new term. I don't know what what number we're on right now. But guess what else there is? VOC. How lazy can I be? Oh, I only did it in one place. Output, whoops, I failed. Okay, put the output, and then this. So again, it's the average of the outputs. Or you can think of it as the offset of the outputs. You know, when you use a sine wave in the function generator, it goes above 0 and below 0. And then when you set an offset, let's say you set an offset of 1 volt, now it goes above 1 volt and below 1 volt. It's the exact same things on both the input and output. There's some average, it's like your offset, and you go above and below that. Okay, how's it going?
I think that makes sense. I like that, what do you call it? Example that you just said.
Yeah, you know how Braun has his rap. I have my disco. This is my. Okay, never mind. So yeah, so we've got those definitions, and now let's get to when you're actually talking about this as a amplifier. There's 2 kinds of gains. One you like, so we'll do the one we like. We like this gain, and this kind of gain is the gain we've been looking at for the common emitter, for the common base, all of those amplifiers. This is the one that corresponds to that one for a diff pair. We like this gain. And more definitions. You have ADM. And if you remember the gains we did for the single-ended input, single-ended output, we called them AV. This A is the same as this A, so it's the gain. But the DM, let's see if my pen decided to come back to life or not. Ah, yay! I really don't understand. Gain differential mode. And this is saying, when you're looking at the gain for differential mode, remember over here for a common emitter, you took V in as your input and V out as your output. And then for the experimental gain, to find the experimental gain of a common emitter, you put one value on V in. So there's this experimental. You put a value on V in and you saw what V out was. And then you put a different value on V in and you saw what V out was. And that's how you found gain. For the differential mode, for a diff pair in the differential mode, your input is not a single voltage anymore. Your input is now VID. So your ADM equals, my bad, you give it VID1. That means you put a value on VI plus and a value on VI minus, and you take the difference, and that's what goes here. So this is actually VI plus minus VI minus, and this is some initial value. And this also is a difference. I'll write it out a little nicer over here since I ran out of space here. But then you'd take this and you'd make the difference between VI plus and VI minus. You'd change that difference between the two, and that would be, and that would give you a different output. And again, the input for a diff pair is the difference between the two inputs. So whereas for a common emitter, it was just the single signal, for a diff pair, the input is actually the difference between the two signals. So you have to use VID here. And if you wrote this all out, you have your V out plus 1 minus your V out minus 1. And that's the output plus and the output minus for an input plus and an input minus. And that's just 1 point. That's just like that's your V out 1 and your V in 1. Then you'd have to change your input difference. And you'd get a different output difference. Okay, up to there? Since the input for a diff pair is considered the difference, you have to use, just for 1 point, you need to use it, you need to have two voltages, V in plus and V in minus, take their difference, and that's that one, that's that first value, V in or V out. I think I should have stopped and not said that. Is that anybody else? Let's see. I can't see everybody because it already popped off the edge of my screen. Is it good? Okay. All righty. So this is the experimental gain. So this is if you're in the lab and you're measuring stuff. But just like the common emitter, where we could have, you know, put a voltage on the input of a common emitter, measured the output, then change the input, measured the output. Just like with a common emitter, this is experimental. There's a theoretical gain. Theoretical gain. Oh, my pen's working. Why am I doing that? And it is, if you remember, the minus GM. In this case, if we had a passive load, it would be RO parallel. Let's get rid of this. This is for a passive load. So that's the theoretical gain. So if anybody asks you for the theoretical gain, instead of, you know, actually building the circuit and measuring nodes, you'd need a theoretical equation like this. So let's do that. We're still on differential mode gain, so let's do that. There's a few ways to do the math for this. And I'm not sure how Dr. Prodnov does it in his section. So I don't know if it pops up in lab, it might be a little bit different than this, but I use a technique called half circuit analysis. So let's find, we're finding ADM theoretical gain. So scroll it down a little bit. Now the circuit we have, since it's a current mirror, the whole thing kind of looks like this, and I'll just write this as V tail. And we have our Vin plus, and Vin minus, V out plus, V out minus, and this is R and R. Okay, so I am going to try to convince you of something first. And this is usually the, so far it's just been kind of definitions. This is another one. It's kind of like gain boosting, that once you see it, it's okay, but sometimes it's hard to see the first time. So let's give this a try. So let's look at a few things. If we're using small signal analysis, one of the requirements is that you're working with things that are linearly related. Okay. So you know that if you look at, like, for example, VGS versus IDS, this graph is definitely not linear. But if you take just a little piece of the line, then it looks pretty linear. And small signal analysis just says, hey, let's take a small enough piece of that line so it looks like a line, and we'll just assume everything's linearly related. Okay. Good to there? Okay, all right. So that's the first thing. So now I'm going to do kind of a proof by contradiction. And we have to go through a few things here. Let's do, let's look at, should have done this earlier, but let's look at, let's just look at a little bit of an analysis of the circuit. Let's say VI plus equals VI minus. Let's say you have some current here. It's either called ISS or I tail in most textbooks. I'll just call it ISS. Let's use ISS here. Okay, if VI plus equals VI minus, in other words, this base voltage equals this base voltage, what's the current going through? Let's call this I1, and let's call this I2. What's I1?
Half of I tail.
Is half of I tail, exactly. And I tail, if we're calling it ISS, over 2. Now that means that if the base voltages are equal, the emitters are tied together, so the emitter voltages are equal. The base voltages are equal. That means you have the same VBE on both sides. And the resistors are exactly the same, the supplies are the same. So both sides are identical. So they have to conduct the same amount of current. And you know those two currents have to sum to ISS. So you know each one has to be ISS over 2. Okay, so you know that. Whoops, what did I just do? Okay, so in that case, let's say there's a voltage on here. We'll call it Vn. And here's my, so let me ask you one more question. Let's do one more question here. Let's say I make Vi plus just a little bit, let's just add, let's make that your VIC, remember the average, plus just a small voltage, which means if it's a balanced input, that means the other side has to go in the other direction. Okay, so now what do you know about I1 versus I2?
I1 is greater than I2.
I1 is greater than I2. Okay, so now we have a little more current going through the left side than the right side. If you add up I1 and I2 now, what do they sum to?
They still sum to ISS.
Yeah, so ISS, that is fixed. You need a really good current source here. And I1 plus I2 always equals ISS. So if I1 goes up, then I2 has to go down by the same amount. Okay, so we have that. Let's cut off the top just a little bit. All right, so next question is, let's do a proof by contradiction. Proof by is that an A? Contradiction. 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 Is that close enough?
Yeah, I think that's right.
Okay, thank you. So let's say this Vn, my claim is that it doesn't move. So by proof by contradiction, I'm going to try to say that if it moves, then the currents won't sum to ISS anymore. That's my goal. So if Vn moves, then the currents won't sum to ISS anymore. That's what I'm trying to prove. So let's try one. Let's say if I move Vi plus, let's say I move that up by delta V. Up by delta V. Okay. Right, up by delta V. That means that, and then let's also say in this proof by contradiction, let's say this also moves up by delta V. So I had Vi plus move and I had Vn move. Okay. So if Vi plus goes up and Vn goes up, what happens to the VBE of, let's call this Q1. If both Vi plus goes up and Vn goes up, what happens to the VBE of Q1?
Stays the same.
Stays the same. So in theory, it's still conducting ISS over 2. Let's say we start with Vi plus equal Vi minus. And Vn and Vi plus goes up, current stays the same. Okay, if this is a balanced input and Vi plus went up by delta V, that means if we're assuming balanced input, that means if Vi plus goes up by delta V, Vi minus has to
Go down by delta V.
Goes down by delta V. Goes down by delta V. Okay, so that's the same question we asked for Vi plus. So Vi plus went up by delta V and Vn went up by delta V, said VBE didn't change. So let's look at the minus side now. So if Vi minus goes down by delta V and Vn goes up by delta V, did the VBE change?
Yeah.
Yes.
What happened to it?
It decreased by 2 delta V.
Decreased by 2 delta V. So that says Vi minus side, it's getting its VB turned down, so its current's changed. If you started with Vi plus and Vi minus equal to each other, you had ISS over 2 going through both sides. This side didn't change, but this side got smaller. So now when you sum the currents, do you agree that they're not going to equal ISS anymore?
Yeah, they won't.
Yeah, this side's still ISS over 2, but this side, because the VBE went down, now it's much less than ISS over 2. Okay, questions? Okay. So if that made sense, then if we change these, for example, let's say I said instead, let's say, let's look at VI minus. The problem was that its VBE got smaller. So let's say, oh, well, that can't happen. Let's say Vn goes down by delta V. So when I move Vi minus down by delta V, let's say Vn goes also down by delta V. What happens to the VBE on the Vn minus side?
Stays.
It increases this
It
time.
stays the same.
It stays the same on the minus side. So you still have ISS over 2. Then what happens on the plus side? You were already over on the plus side. What happens to the plus side? Vi plus goes up, Vn goes down.
And it decreases on that side by delta V. Or
Okay.
2V, sorry.
Yeah, it actually goes up by 2 delta V.
Yeah,
Now it's,
sorry.
yeah, no, yeah. So now it doesn't sum to ISS anymore. So the only way you can argue that it's still going to sum to ISS is if Vn doesn't move. Okay, so this is this proof by contradiction that I didn't write the second half of it, but your result is, and the pen stopped working again. The conclusion, what do you say at the end of proofs? It's been a while. QED?
QED.
QED, okay, QED. Vn doesn't move. Okay. And that makes the math really nice. So let's go and try to, let's see what that means. I'm going to draw this one more time.
Professor, sorry, what were we trying to prove again? Sorry.
Okay, so in most operation of these circuits, the input will be balanced.
Oh, okay.
And when the input's balanced, we want to know whether this node moves or not. Whoops, it stopped writing again, I'm sorry.
No,
That node right there, we wanted to know if that moves or not. And it's still not clear why, but that comes in a second, if I can get my pen to work. Let's see. Nope. All right, back to the mouse. So VI plus, I should just cut and paste. So I'm not sure. VI plus, okay. All right, and Vn minus. Minus. Okay, so if this node doesn't move, in small signal analysis, when a node doesn't move, what do you get to do to it?
Ground it.
Ground it. So what you can actually do here is, if you really want to do small signal analysis, you have to replace the transistors with, the small signal model and, find V out over V in and all that. But let's see if we can make it easier. Because that node doesn't move, because, I don't want to write all this out without a pen. Because Vn stable, nah, doesn't move. I want to make it clear. Doesn't move.
Professor,
Yes?
all those all the VNs and Vouts on that circuit, are those capital Vs, right?
Yes.
Okay.
Yeah. Thank you. Okay. So if you ground this node, what's this circuit?
It's a common emitter.
Yes, and you're done with finding the gain. Let's do this a little bit more formally. There's also this common emitter. So you actually have two common emitters, and you say, oh my goodness, well then if this side gives a gain of, remember the gain of a common emitter So I'll write that as AV, not ADM. So this is just for a single common emitter. If AV equals GMRO parallel R, then, oh my goodness, this side has this gain, and the green side also has that gain. So wow, this must have twice as much gain as a common emitter because one's going up and one's going down. So this must have twice the gain. This is where definitions come in again. And the definition says, oh, it's writing again. This is so weird. I don't know. It's so the definition of VID is that if you're comparing it to a common emitter with an input of Vn, so let's say you had a common emitter over here, and you're trying to compare the gain of these two circuits, and you had Vn right here, and that's your V bias plus some small signal, some little moving signal. If you're comparing that to, actually let me write it a little bit different. Your VI plus here is actually VIC. So again, that offset. And if you want to compare it to the common emitter, you take half of whatever you were giving the common emitter and put it on the plus side, and half of what you were giving the common emitter and putting it on the minus sign. So again, it's just a definition to memorize, unfortunately. And now if you subtract VI plus from VI minus, what do you get?
Vn.
Vn. And now you can say, well, I know the input to the diff pair is actually the difference between the two inputs. And if I want to compare the diff pair to the common emitter, I want that difference to actually equal whatever I was giving the common emitter. So to do that, you give half of what you were giving the common emitter to the plus side and half of what you were giving the common emitter to the minus sign. Then when you subtract them, you get Vn as your VID. Was that too many words? Okay. So if you give half to one side and half to the other, the theoretical, we're finally there, the theoretical ADM, so the gain of the diff pair, the differential mode gain, is actually GM of your input transistors, RO parallel with R. Because you're only moving the input half as much on each side, so the output only moves half as much. So one's moving half up and the other's half down. And then if you take the difference, you get the gain that you got with the common emitter. Okay. So let's see. Questions on this? There's one more gain, but I won't be able to explain it completely. Let's see, where's the homework? Homework. So
I actually have a question.
okay.
So that Vn, the one that we come to conclude from Vi plus minus Vi minus, that, like, I can't see that in that circle right there where it would be inputted. Like how would you view that as coming into the circuit?
Okay, so you'd have your VIC. So the circuits would be sitting at rest. If you have a diff pair, that's just the bias voltage. That's the same as the bias voltage you had for the common emitter, where you made the current mirror to set the base voltage to get a certain current.
Okay.
That's the same as VIC for the diff pair.
Okay, that makes sense.
And then what you do is, for a common emitter, you would just move the bias voltage, go above the bias voltage and below the bias voltage.
Okay.
And you move it up V in. If it's lowercase, that means delta V. So you move it up some delta V.
Okay.
on a common emitter. But on a diff pair, because both sides are amplifying and you want, well, actually, I shouldn't say that, because the input is actually the difference between the two inputs, you take half of that delta V and put it on one side and half and put it on the other. So it's actually
Okay.
VIC plus delta V over 2, VIC minus delta V over 2. So
Would you do that with like a voltage divider? Or something?
you could, but if you have there's so many advantages to using a differential circuit. If you're using this as anything other than an input, actually, I started talking about other circuits and maybe I shouldn't do that. But this circuit shows up inside receivers, all sorts of things. When you're doing like an EEG or an EMG or something like that, you have like the 60 hertz noise on your body, and the signal also has 60 hertz noise on it. If you gave that to a diff pair with that 60 hertz noise on it, that 60 hertz noise would disappear
Oh, because it's subtracting it out.
on both sides.
Yeah. Okay.
Wait, what was your question again? I'm sorry. I started went off.
Just I think you answered it. It was just like how you connect that VN signal to that circuit that you drew right there. Like the wire, if you have a wire that's connected to some VN source, where you would plug it.
Okay, actually, let me give you a better answer. And that is that our whole goal of building an op amp is so we can connect it up with feedback.
Okay.
And the feedback actually fixes its voltage so it's appropriate against the VN plus.
Okay.
So if you had, I'm not going to get to the last topic. That's okay.
I can ask you after class.
Yeah, that's okay. This is good because if we're here, we should talk about it. And so if you have something like this, so like a non-inverting op amp, this would be your minus input, this would be your plus input, and you really don't have to, as you give it this plus input, and the feedback actually fixes itself.
Okay. I see.
And then you don't even have to worry about the minus terminal, the inverting
Okay, so
input.
the way it's set up, that condition that we just proved by contradiction satisfy itself the way the circuit is set up if you were to plug in V in like you just drew right there. Okay.
It's kind of magic. It is truly magic.
Okay. Thank you for the explanation.
Okay, let's see. How should I do this? Okay, like I said, the last topic, I didn't get to common mode gain, which is my fault. Wednesday, I thought it would be fun to improve the circuits with the compound transistors, but kind of didn't give me time to cover common mode gain or cascading amplifiers. The cascading amplifiers, that's a very quick one. That's a video less than 5 minutes, easy. Common mode gain, that's probably a longer video. But is there a protest if I ask you to watch that for the homework?
No,
No, not at all.
I think that's fine.
Yeah, no.
I don't think so.
Yeah, no, that's not a problem.
Okay, all right. Thank you. You're very kind. Okay. But and then the last question is, if I send an email out and ask like various ones of you to record a video of you saying a word or a sentence, would you be willing to play for the banquet entertainment? Okay. I have one person, so I'll send it all to one person.
I'll do it.
Yeah, I'll do
Cool,
it as
cool.
well. I don't mind.
Awesome. Okay. Thank you. I'll try to make it, I kind of crashed and stalled, but I'll try to drink some caffeine or something. Get it back on course.
Easier.
What's that?
We're trying to make your life as easy as possible. No.
Thank you. No, you all, I bow in respect, and yeah, so sorry for all that's going on, and hopefully you're all doing okay. It just makes me cry when I think what's going on around. So thank you for your patience with us also.
Thank you.
All right.
Yeah, thank you.
Thank you.
Spencer, why is your picture different?
I don't know. I just keep changing it to different views.
I don't think that's what you look like. I'm pretty sure.
I mean, I'm getting there. I have a really gnarly mullet right now, but
Do you?
yeah.
But again, my 523 class, there's one guy that his hair just grows really fast, and every week it's like it's bigger.
All right, I'm gonna
Right.
leave.
Right.
Have a good weekend.
Bye. You too.
Yeah, thanks, Professor.
All right. See you later.
Yeah, have a nice weekend.
All right. You
Thank you.
too.
Thanks,
Question,
Professor.
All right. Bye-bye.
I had a question, Tina.
Mhm. I don't know.
Oh, sorry. Can you see me?
Yes.
I had been studying for 329 and completely forgot about our 2 o'clock lecture. Do you have a 3 o'clock lecture also?
Yep.
Okay, cool.
And I'm recording. Thanks, Damani. Thank you so much every time. What would we do without you?
Okay. Appreciate it. Yeah. I just like being in the lecture because I feel like it's more interactive. But yeah, the recording's
Okay.
cool. Oh,
Yeah, I just talked at you today, so it
Okay,
wasn't all
well,
that interactive.
okay. And is it with the same Zoom link?
Yes, you're in class.
Okay. Currently in class then. Yeah, I know. Zach texted me. He's like, "Oh, so you're just not going to show up to Tina's class?" And I looked at the time. I was like, "Oh my god!" Yeah.
Yeah, I got all excited Wednesday because I thought it would be really neat for you to use the compound transistors to improve the circuits.
Mhm.
And then it took so much time. I got behind on homework topics, so
Right.
I kind of had to talk today really fast.
It's okay.
Y'all are so nice. I don't know if I'd be as generous as you all. Hey, people, come here. Bye. Give me a hug. Oh, no, nap time.
I'll start doing it.
Yeah. First day. Yeah. So hi. Let's see. So I spent too much time on Wednesday on the compound transistors. So I kind of got behind on the topics for the homework. So the other class was okay with me making, I think we can go pretty fast here. If I use the notes from the previous section, I'll try to go slow enough so those taking notes can follow along. But if I do that, because my pen keeps crapping out and not writing, I don't know what's up with this pen. It just randomly starts writing and randomly stops writing. If I use the notes from the previous section, then I can go faster because I don't have to deal with the broken pen. Okay, which means we'll probably get through the topics. But if we don't, then I'll do a quick video so you can do that for the homework. But I apologize for my time. I just can't tell how long things take, and you should probably be really happy that you're not taking one of my midterms, because I always think, that's an hour, that's a 45-minute exam, and then 2 hours later it's like, yeah. So all right, I'm already sharing. Didn't realize I was already sharing. Can you all see, just to make sure? Again, I don't have the green rim around it like I usually have. Okay. All right. So today's topic is diff pairs. And we talked last time about the DC part of it, I think, in our section, right? How this, oops, come on, right. Okay. So this, a current source is actually, it's that whole current mirror. Get up like this. And this node right here, let's put this node right here would be this node. And all of the circuitry would be inside that current source. Okay, so to have this amplifier be happy, you need all of your transistors to be in the forward active region. For this one to be happy, you need that VCE sat. So this node right here has to be at least VC sat to make the tail current source happy. And then to make this transistor, you need a VC sat across here. Let's try the pin. If it's still working, then it's still working. So the lowest V out plus can go, or V out minus can go, is 2 VC sat, because you've got one VC sat to here and then another one here. And then the lowest V in can go is lowest, this can go as VC sat, and this is a VBE on. So the lowest V in plus or minus can go is VB on to keep all the transistors in forward active region. So I think we did that last time. Is that right? Kinda? Okay, but anyways, this is a diff pair. And this is called the tail current source. And in textbooks, they generally write this current as either ISS or ITail. And that's this right here. Other things to note on here, these resistors are the same value. Transistors should be identical. These two should be identical to each other. This could be the tail current source could be a different transistor. But yeah, the two input transistors should be identical. What else? In lab, you might be going from -5 to 5. So in lab, this, I'm using something like 5 volts here, but in lab, this might be -5 volts instead of ground. And if this is -5 volts, then your input will probably be 0 volts. But since I'm going ground to 5 volts, I picked, just like 0 volts is midway between -5 and 5. Because I'm 0 to 5 now, if I pick the midpoint, that's going to be 2.5. So you want something in the middle between your ground and 5 volts, and something that will give you a VBE on here and a VC sat there. So VC sat plus VB on at least. So the DC parts of the circuit, is that okay? Any questions on that? Okay, so I did make a video with most of this on it, and then I don't think it's posted. So I think I put it into YouTube and then forgot to post the link. But one of the hardest parts of diff pairs is that it has about 1,000 new vocabulary words. So let's just start going through vocabulary words first. First one is VID. And VID is the difference between the inverting input and the non-inverting input. Oh, there we go. I got everybody's picture. Okay, so VID is defined as the non-inverting input minus the inverting input's voltages. So that's the difference between the two inputs. Okay, good. And the D there is for differential. So this D is differential. Okay, and I have this in lowercase right here. If I wrote it with the first letter capitalized and the second letter lowercase, do you remember what that means?
Does that have to do with it being DC or AC component?
Yes. And if it's all capital, what is it?
It's DC, right?
Yes. And if it's all lowercase?
Then yeah, AC.
And then if it's capital first letter and lowercase other stuff.
Isn't that both? Is that when they're okay? Yeah.
Yeah, you got the sum. So if what this VI, if you do capital V lowercase I, what that actually means is that there's some offset on your input. So for the VI plus and VI minus here, remember you're going -5 to 5 in lab, so your offset is actually 0. But if I'm going ground to 5 volts, then you want to make the inputs somewhere in the middle. So you would offset them by 2.5 volts. So this input right here is whatever your offset is plus your moving signal. And I'll get into exactly what that is in a minute. But your inputs, your VI plus and VI minus, it's this DC voltage. And then on top of that, we'll talk about in a second the balanced input. The VI plus and VI minus travel above and below that DC offset voltage. Okay. Questions? No? Okay. So you've got your DC offset voltage, and then you've got your moving signals. There's two kinds of signals that you'll see. There's the balanced input, and I have it color-coded here. I have VI plus as a sine wave. That's the black signal right here. And then I have VI minus as the green wave. And notice that if you flipped VI plus signal, it would be the VI minus signal. So the VI minus signal is going equal and opposite direction. And if it does that, if signal goes equal and opposite directions, then the average is just going to be that VIC. Is that thumbs up?
Yep.
Okay. All right. Okay, so you've got your average and then your VI plus, maybe in the case when VI plus is going up, then the VI plus would go up by a delta V and the VI minus would go down by that same delta V if it was a balanced input. Did you use balanced inputs in lab? So did you have them going equal and opposite?
Yeah.
I think you probably did.
Or, no, we had them the same, didn't we?
Yeah, I think you had one that was set at a DC voltage and the other one moving.
Yeah.
And that, because we don't have fancy equipment, even in the lab, we'd have you use unbalanced inputs. But unbalanced input is when one is fixed and the other one moves above and below it. And that's what you used 347 and in 348 in the lab. And I drew the unbalanced input below the balanced input here. And you have your VI plus, it's doing the same thing as it did before. But now the VN minus, it's staying constant. It's sitting at VIC. It's sitting at your offset. And then the VN plus goes above and below it. Okay, so.
If you were to tie your inputs together like we did in lab,
Mm-hmm.
which one would that be considered?
That would be your VIC.
Okay.
Your VI plus and your VI minus would just always be VIC, because VIC is defined as the average.
Mm-hmm.
So if they're the same voltage, then it's also your VIC.
Okay, that makes sense. Thank you.
Okay, so we've got, I underlined for the other class, I underlined the things that were definitions. So we've got VID, and we've got a balanced input, we've got unbalanced input, and we've got VIC. Those are our definitions so far. Any questions on those? Okay, so next set of definitions. If there's a VID, of course, there's a VOD. And the VOD is the same thing. It's the difference between the outputs. So for the input of a diff pair, the input is actually considered the difference between VI plus and VI minus. And the output is actually considered the difference between the V out plus and the V out minus. So it's not just a single voltage, it's a difference between two voltages. Okay, and then also on the output, turns out the output also, if you have a balanced input, well, even if you don't have a balanced input, even if it's unbalanced input, you'll have a balanced output. And they'll move equal in opposite directions. And if you take the average, they needed a name for that. That's the V output common mode. And it's just the average of the output. Okay. Definition is still good? Okay. Then I just wanted to put, the next thing was just putting a name to VIC and VOC. I've already used them and called them the offset and the average. The official name is V input common mode and V output common mode. Just means the average. When you hear a common mode, it just means the average. Okay, we're going to be, yeah, we'll have plenty of time to do the other topics if they all go this fast. Right about now in the last class, I think I was swearing at the pen. Good on definitions? Okay, all right. So diff pairs can also be used as amplifiers. So we want to be able to talk about their gain. It's kind of weird. It's like you've got all these moving parts here. You know, how do you figure out the gain? The gain is the exact same definition as it was for the common emitter. So the common emitter is you give it an input, find the output for that common emitter, then give it a different input and find the second output. And then you subtract the outputs and put that over the difference in the inputs. Did that work in the air? Kinda? Okay. So for a common emitter, you have experimental gain. And if you're in the lab, what you would do is you'd put a value for V in on your common emitter and see what the V out is for that input value. And then you'd change V in, you'd put a new value on V in, and you'd see what your new V out value is. And you take the difference in the outputs and put it over the difference in the inputs. Okay. So differential mode gain, ADM, that's another, I should underline that. That's another definition. ADM, differential mode gain. And this is the gain that corresponds to the gain we've been looking at in our previous amplifiers, which was AV for the common emitter. Differential mode gain. You, again, just take the difference in the outputs for two different inputs. But remember, the input for a diff pair is the difference in the inputs. And the output is actually the difference in the outputs. So it's still, you're taking an input, but just so happens the input for a diff pair is a difference. And then you're taking the output, which, oops, for diff pair, that's also a difference. So you could write it using the VOD and the VID notation. But if you wrote that all out, you'd say, okay, I put this value on VI plus and this value on VI minus. Okay, I need VID, so I'm going to subtract them. And then that gives me these two outputs. And so I subtract them to get my first VOD. And then I change the difference. So now if I just did this, there'd still be the same difference in VI plus and VI minus. You have to change the difference between the two to get your second point. So this is how you would do it in the lab. You'd make all these measurements and plug it into this equation. Is there any questions on that equation? Nope. Okay. Okay, and then, so that's a differential mode gain experimental. So this is experimental. This is experimental. It's the experimental equation. For a common emitter, we went through small signal analysis and we came up with an equation for gain. And that was G minus GM RO in parallel with R. This is what I would call the theoretical gain. So we need to find the theoretical gain here. And you have to go through some steps here to come up with that equation. There's a number of ways to, I know, isn't this thrilling going through lots of definitions? Yeah, this is one of my least favorite parts, is just listing off definitions. Yeah, it looks like a very complicated circuit. You could go through small signal analysis, but it's painful. So I use something called a half circuit. Oh, I didn't write it down on this last class. I use a thing called, what's a good color? Purple. And the pen's not working. No, it's not going to work. Half circuit analysis. And we'll use this to find the other gain too. There's another gain that we need to derive analysis. So you can actually analysis. You can make this a horribly complicated calculation, but you know me, you've seen the math that I've done in class. Do I like horrible calculations? No. So yes, exactly. So I'm trying to get away from that. So let's see what we have here. So some things in finding the theoretical gain. We have to come up with some information about the circuit first before I can use this trick. The first thing is to realize that for small signal analysis to work, we need to have linear relationships between everything. That's why we could use superposition, all that. So anything, so the voltages and the currents, they're linearly related. Yeah, is that okay for a first assumption? And actually, I didn't use that in the last class, now that I mention it. Okay, and then I think maybe we did this too last time, but let's go ahead and do it one more time. So you have your differential pair, and my goal in the next few steps is to make you believe that this node right here doesn't move. I think I don't know, Tristan, did we do this before?
I don't think we did.
Okay.
I don't remember it anyway.
Okay. All right. So my goal is to do a proof to convince you that this node doesn't move. Okay. So let's say Vn plus equals Vn minus. So if Vn plus equals Vn minus, and we have ISS through the tail, if Vn plus equals Vn minus and the R's are equal and these transistors are identical, how much current is going through I1 and I2?
Half of the tail current?
Oh, yeah, it's written right here, isn't it? Should I scroll it down so there's some mystery?
No, I mean, I knew that from lab, but.
Okay. Yeah, so if both sides are identical, you've got ISS going through the tail and the two sides are identical, you need to have the same current going through both sides. So it has to be half of what's going through the tail. And that's ISS over 2. Okay, so that's check 1. Now let's go down, and we haven't got to the proof yet, but just some background here. Let's say I take VI plus, and if these are true, then you can also say this equals VIC. Because VIC is the average, and if both inputs are equal to each other, then they're the average. Okay, so let's say I take VI plus, and its original value is VIC, but I raise it just a little bit. Okay, so now VI plus actually equals VIC plus a little bit of voltage. And because this is a balanced input, if VI plus goes up by delta V, VI minus has to go down by delta V. Okay, so these are your new voltages. And ignoring what's on the side over here, if I put my hand over it, it doesn't hide it. So ignoring what says over here, if VI plus goes up, what happens to I1?
It has to increase.
Has to increase, okay? And if VI minus, if the left side goes up, what has to happen to the current on the right side?
The opposite. Decrease.
Yeah, because it has to still sum to ISS. So if this side gets more current, this side has to get less current, so it sums to ISS. Okay. So that's what's being said here. If I turn up this side and turn down this side, I1 gets bigger than I2, but still I1 plus I2 has to still sum to ISS because that's the only place the current can go. Okay, so let's do a proof by contradiction. Let's say I move VI plus. I don't want to mess this picture up, so let's just copy it. Oh, I wrote over something, so never mind. So let's say I raise VI plus and drop VI minus, just like I said, by delta V. But let's do a supposition that this node, this Vn node, let's say Vn plus goes up by delta V and Vn goes up by delta V. How much did the VBE of Q1 change?
Not at all.
Not at all, because both the emitter and the base changed by the same voltage. So VBE stayed the same. So what do you think happens to the current?
Stay
Nothing.
the same.
Stays the same. And it was ISS over 2 before, when it was, you know, when it, both VI plus equaled VI minus. So you still have ISS over 2 going through the left side. Okay, now let's look at the right side. You've got VI minus, and you've moved that down by delta V. Okay, in this scenario, I said Vn moved up by delta V, so VI minus goes down by delta V, and in this first proof by contradiction, I said Vn moves up. So what happens to the VBE on the right side?
It also stays the same.
But VI plus is moving the opposite direction of VI minus.
So it moves. No, never mind.
It gets smaller.
It's smaller. So Vn, if we assume it's going up by delta V, and VI minus is going down by delta V, VBE just got smaller by 2 delta V. So what happened to the current on the right side?
It got smaller.
Got smaller. This side's still ISS over 2. This side got smaller than ISS over 2. If you add them together, do you get ISS now? No. So that didn't work when Vn moved up. Let's do it the other way. Let's say I move Vn plus up, but assume that Vn goes down. So what happened to down by delta V? So let's say Vn plus went up by delta V and Vn went down by delta V. What happened to the VBE on the left side now? Is it working in the air? I'm not sure. So now we're,
I missed it.
okay, let's say Vn went down by delta V and Vi plus went up by delta V. What happened to the VBE of Q1?
It increases. Oh, yeah, it increases, yeah.
It increased, so the current just went up on the left side, but let's see what happens on the right side. So the Vi minus went down by delta V, but Vn also went down by delta V. So what happened to the VBE?
Stayed the same.
Stayed the same, so it's still ISS over 2 over here, but this side went up. So is it going to sum to ISS?
No.
No. So it turns out if you follow this logic and now try it when Vn doesn't move, then you can see that the only time that everything will still sum to ISS is if Vn doesn't move. So did the proof by contradiction maybe convince you, kind of?
Yeah, that was good.
Okay. All right. So now finally we get to, our whole goal here is to find the differential mode gain. So the good gain, the gain that we try to design for. Oh, and QED. I had somebody help me with that because I couldn't remember it. So if a node doesn't move, actually let's go back up here. If this node doesn't move, what do you get to do in small signal analysis?
Ground it.
Ground it. Okay, so if you ground that node, then whatever happens on the right side doesn't affect the left side, and whatever happens on the left side doesn't affect the right side. So I just circled the circuit on the right side and circled the circuit on the left side. What's the circuit in green? Am I going too fast for those that are taking notes?
No, you're okay.
Okay. Of course, I'll post all this too. So what's the circuit in green?
Common emitter.
Common emitter. What's the circle in blue?
Also a common emitter.
Yes. So a diff pair is basically just two common emitters stuck together, or if you using MOSFETs, two common sources stuck together, and that bottom node doesn't move if it's designed well. And you have a balanced input. Okay. So then you say, well, I already know the gain of a common emitter. And really you're almost done, except, hey, a diff pair wouldn't be complete if there weren't like 20 more definitions. So let's do one more definition. Remember that the input to a diff pair is the difference between the inputs. Is that okay? So the official input to a diff pair is VI plus minus VI minus. Okay. For a common emitter, your input is just how much the base moves. So you have whatever your bias voltage is, plus that little moving signal on top of it. So you've got your biasing circuitry that sets the base voltage, so you can set the current in your amplifier, and then on top of that you put a little moving signal. Okay. So here's V in. Now, if you want to compare a diff pair to a common emitter, you want the input to change the same amount. But what's the input for a common emitter is just V in. But what's the input for a diff pair again?
The difference of Vn plus and Vn minus.
Yes. So that difference has to equal Vn. So if you're using Vn on your common emitter and you want to compare gains between the common emitter and the diff pair, the difference between the inputs has to equal Vn, has to equal that signal that you're giving to the common emitter to compare apples to apples. So what happens is that you actually define the inputs of a diff pair. If somebody says, give your diff pair a signal of Vn, what you do is you put half of Vn on one input and half on the other. So you actually get Vn over 2 plus Vn over 2 and minus Vn over 2. You've got your offset on your inputs. It's 2.5 volts for the first drawing I did, but in lab it's probably 0. And then if you're trying to have a signal of a half a volt, you put 0.25 on one side and 0.25 on the other. Okay.
So the Vn that we're putting in that equation, that's the Vn that we're using for the emitter? Or that's the
common emitter, yes.
Okay. That makes sense.
Yeah. You say, oh, what's the small signal input for the common emitter? Oh, it's this much. For the diff pair, now you have to put half of that on one side and half on the other. So when you subtract them, it comes out to that same value. Okay. Let's see. So because you're only putting half the amplitude of the signal of the common emitter. So if you only move the input half as much, how much does the output move?
Half as much.
Half as much. And so you have one side, the output's moving up by half as much as a common emitter, and the other side, the output is moving down by half as much as a common emitter. When you subtract them, what do you get? Compared to the common emitter? That's a
You
hard
get
question.
the same thing, don't you?
Yes. So it actually turns out that because of this definition of only putting half of the input on each side, and the output's only moving half as much on the diff pair, that when you subtract them, you actually get the exact same gain as a common emitter. So the gain of a diff pair equals the theoretical gain of a diff pair equals the theoretical gain of a common emitter, or the magnitude, I should say. One thing you might see here is that I don't have a minus sign. That's because I called this V out plus and this V out minus. So when I move V out plus up, V out plus also goes, V in plus up, V out plus also goes up. So the minus sign goes away. If I had just named this differently, if I had named this V out plus and this V out minus, then I would have needed a minus sign here. If I would have just switched the outputs. Okay. My ears can never take an hour of this. All right, so we've got all those definitions, and then we've got the equation for experimental gain for diff pair, and then we've got an equation for theoretical gain of a diff pair. So any questions up to there? Okay, so now for the most painful one. Most painful definition is, what number are we on? I think I just stopped numbering, didn't I?
I think it's technically number 5.
Technically number 5, okay.
Or maybe not, maybe it's just,
Oh, ADM was 4, oh, okay. I should have named this A or something, right?
yeah.
Okay, 4, okay, we're on definition number 5. ACM. And let's see if I can steal one of these pictures instead of having to draw. This is good. This is one of the ones that I'll post for the other class. Is it really windy and slow? No. Has it been windier? I was wondering if there's some weird thing because all the pollution went away, that the earth is having a party or something. Okay, ACM. All right, so ACM also has, yes, my pen's back, has an experimental definition and a theoretical definition. The experimental definition is ACM. Oh, I should say what this stands for. A, again, stands for gain. Just like AV was the gain for a common emitter, ADM is the gain for a differential mode. ACM is the gain for common mode. Okay, and common mode, again, is just equals average. Average. Okay, so if you have a VI plus of this and a VI minus of this, you add them and divide by 2, and that's your common mode value for those two signals. Okay, so oh goodness, I should do it. Oops. Well, I didn't mean to erase that. All right. Let's do one more definition before we get there. So I didn't give you an equation for VIC. VIC is VI plus VI minus all over 2. We're done. It's the average of the inputs. And then VOC was the output common mode. Is VO plus VO minus all over 2. So again, just the average of the output. Okay. So the common mode gain, your ACM, your ACM equals your VOC1, so your first average. So for some average input, you find the average of the output, and then you change the average of the input. So if you had both inputs at 2.5 volts, you change them both to 2.6 volts, VIC. So you have average of the input, and so you find the average of an input and see what the average of the output is, and then you change that average, and you see if the average of the output changed. Okay. Since we have so much time, let's look at this for a second. Let's say VI plus for VI plus equals VI minus. Tell me, so the V out plus and V out minus, they should equal each other if the VI plus and the VI minus are equal to each other. What are their values? Let's call this VCC.
$2.5.
What's that?
2.5.
Not for the V outs.
Oh, the V outs, excuse me.
Yes.
Isn't it VCC minus IS over 2 times R?
So you know the current going through both sides. That current's being forced through the resistor. That gives you a voltage drop, which gives you your outputs. Okay, and let's say this equals 2.5 volts. Okay, so that's test number 1. So we have our output and we have our input. Let's check this out. Let's say for VI plus equals VI minus equals 2.6 volts. What's my V out plus and V out minus? I just changed, do you agree that I changed the average of the input just now? Okay, it used to be 2.5, and now I just changed the average to 2.6. I moved both V in plus and V in minus up, so now their new average is 2.6. What's my output voltage now? My V out plus and V out minus.
Is it not the same?
It's exactly the same. CC minus ISS over 2 times R. So if you find that the ACM, if you find the ACM for this, your output voltages are the same. So if you subtract the same thing from the same thing, I guess I should write it for anybody watching this later. ISS over 2 times R minus C minus ISS 2 times R. And your first average of your input was 2.5 volts. And your second average of your inputs was 2.6 volts. So what's your ACM?
0.
0. And that's awesome. And the reason why it's so awesome is that this has 2 inputs. And sometimes these wires are coming from far away. back when lots of network wires were, a lot of computers, like networks were wired networks, you'd have these two wires coming across the floor and they'd pass by some piece of equipment that would put noise on them, and they'd travel and get some other noise on them. But when two wires are near each other and they get the same noise, they have noise in the same direction. So let's say you had a 1/10 of a volt noise. Let's say your two wires passed by a cell phone or a TV or something, and they both got some noise on them. Relative to each other, they wouldn't change. I'm trying to, that's really hard. Relative to each other, they wouldn't change. But if they have both have the same amount of noise on them, can you see that the average is changing then? And what this says is with a diff pair, if the average changes, it doesn't affect the output at all. It doesn't change the average of the output. So if the average was here, even if these go like this, the average is still here on the output. And that's super powerful. And that's why these circuits, diff pairs, are so powerful in analog circuits, because any noise that happens to both wires just disappears. It gets subtracted out. And it's also, for example, I gave an example in the last class as somebody asked a question, but EEG or EMG, we've got this 60 hertz noise on us. We're really good antennas. So all the equipment around us and lights and everything, we're receiving 60 hertz noise all the time. So if you're ground, let's say your body has 60 hertz noise and your heart signal has 60 hertz noise, they subtract out, they're gone. So it's pretty cool technique. Okay. Right, so is the experimental definition okay? Okay, so that's experimental. Let's go with theoretical. So now we've got, let's see if the pen's still there. Theoretical, pen's gone. Theo. Okay, ACM. Okay, this is a little more involved, and I'm hoping I can do this well in 5 minutes. But let's see. Ah, good. Still there. Okay. So for theoretical gain, you actually use it's a different half circuit analysis, but it's still half circuit analysis. So this is still half circuit analysis. If we do this, half circuit analysis, but it's a different half circuit analysis that we did last time. So this is for ACM. So the last time we said if we have a balanced input, that VN doesn't move. But it turns out if both inputs move, let's do another proof by contradiction. So now let's assume that VN doesn't move. So let's do, come on, pen. Come on, pen. Come back to life, please. Please. Okay, so let's do another assumption here. Let's say, this is another proof by contradiction. And let's say Vn doesn't move this time. Okay, and so we have Vn plus and Vn minus. Let's assume Vn doesn't move. Okay, so I have some VBE and I have ISS over 2 through both sides. And let's say I move both up. So I've changed the common mode. I've changed the average of the inputs. And let's assume Vn doesn't move. What happened to the current on both sides?
Goes up for both of them.
Goes up for both of them because you've just increased the VBEs. So is it going to sum to ISS? No. So actually that VN, when you're moving the averages up and down, that node actually follows. So for common mode signals, so when you change the average of the input, that node does move, but when you have a balanced input, VN doesn't move. Okay, 2 minutes. I'm not going to be able to give this proper treatment, but let me keep going. No, it's back, it's back, it's back. We have hope. So we assume that node moves, so we can't ground it anymore. But here's my quick version. So what's the resistance you see at a collector of a transistor?
Or not.
Or not. So this, it turns out that with this being a biasing voltage, this actually simplifies down to just R naught. So I'll put my V in plus here. V out plus, V in minus. Okay, so this is my, this circuit is now half small signal and half large signal. But if we did small signal analysis, that would look like RO. So here's my claim. Let's do, do you agree that nothing's changed?
Yeah.
Okay. Do you agree that the voltage across these two resistors are the same?
They should be.
Okay. And so that means their currents are equal. So you'd have ISS over 2 going through that way, ISS over 2 going through there. Then you'd also have ISS over 2 going through here and ISS over 2 going through here. Do you agree with that? Okay, so my next claim, it's 4, darn it. I'm almost there, I'm almost there. If you have to go, I'll of course post the video. My next claim is that if I erase this, nothing really changed in the left and the right. Okay, so my claim is that if I move VI plus and VI minus together, I claim these two outputs will still move together. Do you agree with VI plus and VI minus? Okay, then my last and final claim is that the common mode gain that checks for changes in average is actually the gain of this amplifier right here. And what's the name of this amplifier?
Common emitter with degeneration.
Common emitter with degeneration. So your common mode gain, I'm sorry, so sorry. So your ACM theoretical equals, actually your GM gets smaller. So you have a negative GM or positive depending, actually has it written that way, plus 1 over 2 GM RO times your RO parallel with R. Your GM gets absolutely destroyed by this thing. And I'll slow down on the video. I'll do, how about if I just do a short video to explain this last step. But this gain right here is almost 0. So this is the theoretical common mode gain. All right, any questions? I'm sorry I went over yet again. I'll do the last topic for the homework is just a really short video. And so I'll do that. That's like a 5-minute video to watch.
Thanks, Tina.
Okay, any questions?
I don't have any. I'm good.
Okay. All right. Thanks again. Yeah, and if I hadn't spent the compound transistor stuff on Wednesday, that time on that, then we would have got through. But I apologize.